Right, so this is the last thing we're going to look at for today's lesson before I give you a chance to go and practice some problems of your own. And this is linking back to the, the condition we talked about earlier. So we've got a situation here where a motorcyclist wants to complete a stunt. I'll try and link you to some YouTube videos where this is actually done. This is a real stunt. It's often done mainly in the States, but you do get it done here as well, where a motorcyclist completes loop the loop. This is usually done in a cage, but just to simplify this problem, we'll just imagine it as if it's one motorcyclist on a track going around a loop the loop like that. And the question we're asking here is, what is the maximum speed the motorcyclist must be travelling at the top of the loop there to complete the loop successfully? This is similar as well to the video we looked at on Thursday of the man running the loop. So it's a similar sort of problem. What I would like you to do here before I work through this problem is I'd like you to pause the video and I'd like you to try and label the forces on the motorcyclist at the top of this loop and then write out the condition that we've been applying for circular motion. Okay, so let's have a look at this then. At the top of the loop, let's try and label the forces. What forces are acting here? Well, first of all, we've got the weight of the motorcyclist going down, as it usually does, and we've got one other force. That force is also acting down towards the centre of the circle, and this is our reaction force acting towards the centre of the circle. We then apply our condition, force in minus force out equals, or which one does it make sense to use in this case? We want the minimum speed, not anything to do with the angular velocity, so we want the mv squared over r version. We then look at the force in. What are the forces acting in? We've got the weight, mg, plus the reaction force from the track on the motorcycle, r, minus the forces out. What are the forces acting out? There aren't any, so that term's not going to exist, and that's going to be equal to mv squared over r. Now, we're trying to work out the speed here, which is given by the letter v in that formula. And it's important to remember here, this little r and this big R are different. This is the radius of the track, which we've been given in the question to be 2.5 meters, and this R represents the reaction force. We've got two unknowns and one equation. We don't know V and we don't know R at the moment. So that's going to cause us an issue. But this then comes back to what we were saying about conditions and thinking about the problem. We've been asked for the minimum speed. And we know that anything above that minimum speed, the motorcyclist will complete the loop without a problem. But we've got to think about what we mean by completing the loop. And what we mean by that is for the entirety of this track, the motorcyclist must stay in contact with it. So what does that mean? That means that this reaction force has always got to be positive. This R must always be greater than 0. Why is that the case? Because this reaction force here, no matter where you are on the track, must always act towards the centre of the circle. That reaction force can't act to pull the motorcyclist back up on the circuit. So that R has got to be greater than 0. So what does that mean for our problem? It means that we can say at point where the motorcyclist is just in contact with the track, we can say R is equal to 0. At the point where R is equal to 0, it is at that point where the motorcyclist is just about to fall off the track. Any slower and the motorcyclist would not be in contact with the track anymore. Anything greater and the motorcyclist would be in contact with the track. So we then substitute that into our formula. So mg equals mv squared over r. Worth checking here, both these masses do refer to the mass of the motorcyclist and the bike, so it cancels. And we can then rearrange this equation to find that v is the square root of rg. We can substitute that into our formula, noticing it doesn't depend on the mass of the motorcyclist and the bike, it's just the speed which is going to affect whether that motorcyclist stays in contact with the track. So you've got 2.5 times by 9.81 square rooted, and that gives you 4.95 meters per second. So just to recap there, we've said we're applying the condition for circular motion which needs to be met for the motorcyclist to stay on the track. We've done our familiar thing by saying what forces are acting in, what forces are acting out. When I mark these questions in exams, the majority of errors are by getting the signs wrong. So say having mg minus r here, for example. So that's why this rule is really important, as well as labelling the forces correctly. We've then said that for the motorcyclist to be in contact with the track, R has got to be bigger than 0. There's got to be a contact force there. And then we followed and said that at the point where it's just in contact with the track, that R, or it's just lost contact with the track, R is going to equal 0, which then allows us to solve this equation. So I'm going to set some extra problems on Teams for this. I'd like you to work through the questions that I set on Thursday, and then on Tuesday's lesson, we'll look at one more different scenario for this.